Hello, everybody. We'll be presenting our project on Surface EMG Armband for Bionic Hand today. I am Jake, and I'm presenting with Jay, Dan, and Sai. So our project is in partnership with a club on campus called Give a Hand, which works to do a lot of different prosthetic hand projects on campus. The objective of this project is to incorporate with the Bionic Hand project that this club has, where we want to take the current sEMG sensor that they're using and giving them more information through the use of designing a custom armband.
Yeah. So this was the our major inspiration for mechanical design. You can see it's like a commercially available MyoWare EMG sensor version 2. This has a key advantages like it fits most the average forearm, holds the electrode in place with the consistent spacing. It has IMU, but for our use, it's kind of a useless. So we are not going to use IMUs. We have few key differences as well. Instead of dry electrodes, we are using gelled ones since it's a prototype. So we are going to use gel electrodes. And we are using one more electrode for grounding purposes. Yeah. So you can see this is our render design and you can see the actual version of that. It's kind of a loose right now, but we already developed a new version of that and it's kind of more aesthetic. But yeah, this seems to work really fine. So that was the mechanical part.
So the objective of the electrical aspect of the project was to obtain what is called raw output, which is also referred to as the voltage difference between measured and within the measurement and the reference electrodes. A challenge would be to install the filters along with the electrodes in a compact manner, and the purpose of that is to reduce noise and to increase the complexity of what we are trying to obtain. So, an overview on the software, the user is prompted to position his hand in a rest and flexure position, and it's iterated over 10 or 12 tries in order to sort of obtain a reference which can predict the position of a person's hand with respect to the inputs that are provided.
After the analog signal processing component done with the hardware circuit design, there was also a digital signal processing component housed on the Arduino. Using a paper that we had found that implemented a novel Arduino-based real-time filtering method using the feed-forward comb filter, we were able to successfully filter a raw sEMG signal seen in the top subplot of this figure by first removing any remnants of low-frequency noise in the 0 to 20 hertz frequency range, removing any of the power line interference at 60 hertz in its harmonics, and then full wave rectifying the signal by taking the absolute value of it. This is a computationally inexpensive algorithm that can run on resource-constrained hardware and processes signals in real time, assuming that we have a sampling frequency of 1 kilohertz. We also performed a simulation of signal analysis and inference using a publicly available dataset that very closely matched the parameters that we had laid out in our circular armband. The goal of this was to test out binary classification of actions across able-bodied users with clenching and unclenching, and then multiple classification of 4 or 5 different motions like 3-finger abduction and 5-finger abduction. To do this, we use machine learning models that are overviewed in the next step. Here we use the linear discriminant analysis algorithm, first across all subjects randomly and then stratified subject by subject, where we saw that by tailoring each model to each subject's signal characteristics, we could improve accuracy, which makes sense. Each subject has different signal parameters like signal amplitude and characteristics that tailoring the model to that, like what we were trying to do with our calibration program, will yield better classification results. There's also a significant trade-off between the computational power required to compute different window sizes and the accuracy. And as a result, there's a trade-off in what we can accomplish. These issues are only exacerbated by multiple classification boundaries. A linear classifier like LDA struggles with high dimensional data, and to compare that with a nonlinear classifier like a support vector machine, it's significantly worse. However, the SVM is incredibly computationally expensive, even on a dedicated CPU that's much stronger than Arduino Nano, which means that if we want to come up with multiple decision bounds for multiple different motions, it's going to be a challenge on resource-constrained hardware like an Arduino.
To wrap everything up, we've successfully created a mechanical design, which was our armband design that we had mentioned before, that incorporates 8 electrodes around the arm. We have an electrical aspect of the project, which is working on processing and filtering out the signal that we get straight off the electrodes. And finally, our software team has worked on visualizing and preparing the data to hand off back to the original team. The next steps are to successfully hand off all of this to the club on campus. That'll allow them to extract all this extra info off the arm and implement it into their new algorithm. Thank you for listening. These are our references.